Hmm.
Harika olur. Benim açık olursa.
Good afternoon. In this session, in the afternoon session, we will start with invited speaker from Japan. I think Lauren Takahashi. His title is Unveiling the Methane Oxidation Reaction Network Using Graphene Theory. Lauren, are you ready?
Hi.
Hi.
Yes, I'm ready.
If you are ready, you can start.
Okay. Thank you. My name is Lauren, and now shall I share my screen? Let's see. Share screen. PowerPoint. Okay. Can you see my screen?
Yes, yes. Would you please continue? All right.
Okay. All right. Thank you. So thank you for inviting me to speak today. My name is Lauren Takahashi, and today I'm going to be presenting a title entitled Unveiling the Methane Oxidation Reaction Network Using Graph Theory. And here's just a quick background of my work. I've gotten degrees at the University of Arizona, as Gothenburg University and University of Tokyo, and in information science and chemical engineering. And currently I work at the Hokkaido University in the chemistry department focused on research in materials and catalyst informatics. So whenever in this particular work, we are focusing on the oxidative coupling of methane reaction, or the OCM reaction. And here you can see the basic formula for this reaction. And one of the things that we are interested with this reaction is the ability to obtain ethylene from methane. And ethylene is a very important chemical component within the industry, and it is used in industrial applications worldwide. And for some examples, you see it is used for polyethylene, which is for lots of plastics, like our grocery bags, trash liners, and those types of packaging films and plastics. It's used in ethylene oxide for detergents, cosmetics, paints, cleaners, antifreeze, and even pet products, as well as fibers and food containers. And is used for styrene, which is used for packaging and insulation, as well as rubber for tires and footwear. So just from these products itself, this is shown that this type of product is extremely high demand worldwide. Unfortunately, with this particular reaction, directly converting methane into ethylene and other similar products is extremely challenging, and it's challenging for several reasons. One is that this reaction requires very high temperatures, and typically these temperatures start from 750 degrees Celsius and goes up to 950 to even 1,000 degrees Celsius. This reaction also produces very highly reactive intermediate products that often will interfere with the reaction as it carries out. And not only are these products highly reactive, but they interact with other produced intermediates, and they end up producing very undesirable byproducts, such as carbon monoxide and carbon dioxide. And here's an example of some common byproducts of this process. So when we combine methane and oxygen together, oftentimes you'll see byproducts such as oxygen, ethane, ethylene, carbon dioxide, water, OH oxides, as well as methanol. And from here, in order to sort of hopefully to reduce the amount of byproducts, it would be ideal to have some sort of reaction map of the OCM reaction. However, a map of this sort of reaction would be too complicated to create. And that is because there's way too many intermediate reactions that would occur not only simultaneously, but they're also unable to be detected using current experimental or other similar techniques. And given these issues, we've decided to attempt to create a reaction network by using graph theory in combination with first principles calculations. Now, in order to do this, we first have to invest a series of molecules in order to see how they interact with each other and would carry out it if we were to simulate the actual reaction. So in order to do this, we chose 28 molecules. And here I have a list of the molecules we start as our we chose as our starting molecules. And we chose molecules such as methane, several C2 based molecules. We have several oxides as well as water, carbon monoxide, dioxide, and hydrogen as well. And these are all molecules that would be typically reported when experiments or other methods of investigating this reaction would report. And from there, we would first need to get an activation energy of this type of reactions that would occur. So what we would do is we would consider all the possible combinations between each of the 28 molecules, and we would attempt to combine them and see how they would interact with each other and what energy it can give. And we do this using GPaw, as well as combined with the NEB method. So for example, if we were to calculate the activation energy for this reaction here, which is methane plus CH, which would lead to C2H5, we would first consider the initial pair of molecules, as you can see above, and then we would continue on to calculate the final molecules, which is below. And then we would apply the NEB calculations in order to determine activation energy for this reaction. Now, when we did this for all of the possible combinations, there were cases where when we attempted to calculate the initial molecules, they would automatically create a new molecule or just result in different pairs of molecules. So in these cases where we treated these as reactions that would encounter no barrier, and decided to determine that their activation energy was set to 0. Now, in order to somewhat better emulate what we would see in real time, we also tried to apply the Arrhenius equation, and this is in order to get the reaction rate constant. And this was in hopes of attempting to address some microkinetics that might be observed when attempting to report results based on the methane oxidative reaction. And as you can see here by the equation, in order to determine the reaction rate, we would need to know the activation energy, temperature, which here we initially defined as Kelvin, and then we also included the Boltzmann constant. Now, as you can see circled here in red, this equation requires the inclusion of steric factors. And what steric factors are is these are additional factors that we as researchers may not be aware of that are playing an effect, but they help balance out the equation. So in order to consider the steric factors, we also included collisional cross sections, which would help us determine the possibility of the actual two molecules interacting and colliding in the first place. And as you can see here, this is the equation we use in order to calculate the collisional cross sections of each molecule. So in order to determine the reaction rate, for cases where the activation energy would be zero or else would not encounter a barrier, we assumed that the reaction rate was equivalent to the collisional cross sections of the initial molecules. Otherwise, our reaction rate was defined as the collisional cross section of the initial molecules multiplied by activation energy divided by Boltzmann constant multiplied by temperature. So here's an example of how this would work. And we use the previous reaction, and we would calculate the collisional cross section, activation energy, temperature, and Boltzmann as listed. And using this data, we're able to determine that this theoretical reaction would have a reaction rate of 0.0322. Now, in order to use this data for a reaction network, we have to pre-process this data. Now, pre-processing requires us to fix the data so that the machine can understand it more in a better manner. And in order to create our network for this reaction, we used Gephi, and it is a commonly used program within the community that is involved with creating networks for graph theory. And this type of network requires the existence of nodes, edges, and edge weight. And if we want to translate our reaction into this graph, we define our nodes as the molecules that are present before a reaction, as well as molecules that result from the reactions. And the edges represent the reaction rates, and the edge weight is considered to be the probability of said reaction occurring. Now, here we have a look at the network that we were able to generate from the data. And I would like to continue on and discuss a little bit further on some things that were able to pull out from this network. Now here, the reaction network, this is for when the reactions occur at 0 degrees Celsius, which would be 273 Kelvin. From this point on, we actually convert the temperature to Celsius in order to compare the results to experimental data. And as you can see on this network, first you have lots of so-called gray nodes, and these nodes represent the initial molecule pairs. And the labeled nodes are the molecules that would result from a reaction or the products of said reaction. And the edges are represented by the lines that connect between these different types of nodes and represent the reaction constant, and their thickness as well as their color reflect the probability of these reactions occurring. So as we can see here on this color scale, reactions that would have a lower probability would begin from like a yellow or orange colored scale. And as the probability of occurrence increases, the color would then move on towards green and then towards dark blue as its highest occurrence. And the same happens with the line thickness, where the thicker the line, the higher probability of said reaction occurring. Now, if we look at how this network is constructed, one thing of importance we see here is the labeled nodes that concentrate at the center of this network. And I've listed here on the sidebar the actual molecules that are centralized in this network. And as we can see here, we have molecules such as methane, ethylene, CH3O, water, H2, as well as carbon monoxide and methanol, C2H4, etc. And their location in this network shows us that these molecules are being accessed at a very high frequency. And what this means is that there are many reactions that consistently result in these molecules, and thus allow us to understand that these particular molecules are products of many different types of reactions that would occur during this reaction. Now, there's another secondary group of reactions that also attract some attention. There's circled here in red and with the their actual labels here on the side. And as we can see here, they may not be centered to the network, but these nodes have also a large number of connections with other nodes. So from this, we can understand that this group of molecules may not have as large number of connections as a previous central group, but they still have a very high probability occurring and are actively showing up through the reaction. There's some molecules of note here that would like to show up. Now, these molecules that are circled in red and starred, these are actually new molecules that had showed up during when we were calculating the various reactions. So these are products that were shown from the reactions that weren't considered at the beginning, those first 28 molecules. And from what we can see here, these new molecules are fairly prominent within the reaction. And considering that they're not often reported as a final byproduct, we can treat these as molecules that actually don't appear as a result of the oxidation process, but can be treated as intermediates that show up during the OCM reaction that are actually affecting the oxidation process itself. So this gives us a glimpse into some intermediate products and intermediate reactions that may be occurring that current technology can't actually detect, or at least current methods of detection aren't able to report these. And we can also see here that with these molecules, these particular ones here have a high likelihood of occurring during the methane oxidation process. And here, these are some of the main ones that we are interested in, but we've also noticed that with molecules such as CO3 also has a very high weight. So we start to see that while some of the molecules are ones that we want, there's other also highly undesirable byproducts that have a high chance of showing as well. Now, this is a quick look at the top 10 reactions with the highest reaction rate constants when temperature is set to 0 degrees Celsius. And as we can see here, these reactions are have a highest probability of occurring through the methane oxidation reaction. And it supports what we observe visually in the reaction network, where C2H4, C2H6, CH4, and CH3O are at the center of the network. Now, we want to verify the results of the networks against experimental results. So one of our teams, experimental teams, were kind enough to go ahead and explore this reaction through several experiments. And here we're going to just briefly look at the results. So as we can see here in this graph, there really isn't so much of reaction observed up until 600 degrees Celsius. And once we hit that range between 600 and 800 degrees Celsius, we see that selectivities such as C2 selectivities, as well as C2H6 and C2H4 actually increase drastically compared to, say, 400 degrees Celsius. But as we see in this slide, the moment you reach 800, there is a inverse result occurring, where once you hit 800 degrees Celsius, products such as CO and CO2 drastically increase, while the selectivities of a CO2 as well as C2H4 drop. And from this, we can understand that temperature ends up playing a very important role on the various selectivities within this process. So now we wanted to see if we create additional networks, how is the temperature affecting the construction of these networks? And here we have reactions with no barrier, and this is set to 0, but from we can see here that especially the molecules circled in red, there's a very high probability that these reactions will be produced instantly. And from here, we can see in these networks that on the left, we have 400 degrees Celsius for the reaction network. And on the right, we have the network at 900 degrees Celsius. And if we take a closer look, we can see that as temperature increases, the actual reaction rates also change. So compared to the 400 degree Celsius network on the left, the network on the right actually has an increase of reaction rates that have jumped up in probability. So we have that cluster of blues and greens showing the higher probability. And we also see that there's more molecules that start to center in this reaction. And what that means is that different reactions start to actually increase in their probability of occurring as temperature increases. Now, we also want to consider how oxides fare in this reaction. And from we can see in this graph, we see here that even when the temperature is at 0, oxygen and oxides are very prominent in this reaction. And we can see here that even at 0, several oxides as well as oxygen are results of reactions that are occurring instantly. And what we can also see here is interesting is we do see an oxygen atom, oxygen, and O3 in this network, but they don't see as many connections, and they have a lower probability of occurring. So when we combine this chart with the previous network, or this network with the previous network, we can understand that because there's not many reactions that result in these atoms, it is very difficult to remove oxygen once a molecule is oxidized. And from here, we can also see that not only is it difficult to remove, but oxidized molecules are actually an essential part of this network. And here you can see that they're circled in red, but many of these reactions are very prominent within the network. And this just goes to show that as temperature increases, the danger of oxides and oxygen affecting the selectivity of, say, C2H6 and C2H4 becomes greater. Now, we can see here in this graph that as temperature increases, we also see that C2H6 and C2H4 becomes more essential to the network. And what we can see here circled in red is they're very centered and they're connected to reactions that have very high probabilities. And this also happens when reactions do not encounter a barrier, as we see on the left. And when we compare these networks, we can see that both of these molecules are resulting from high probability of reactions, but given their placement in the network, we can now understand that C2H6 results from less reactions overall. And finally, we'd like to look at methanol. Now, methanol is interesting because this is also a desirable product, but this is one that's also fairly difficult to isolate, and we wanted to look at why. So first, we wanted to look at the possible intermediate reactions that would result in the development or the creation of methanol. And here we have a small network, and it has 31 nodes, 78 edges. And here we can see with orange has no barrier and purple is with reactions with a barrier. And as we can see here, most of the prominent reactions that would occur mostly occur without the presence of a barrier, which is good if we want to have something produced. But now when we see or at the reactions that result in methanol being broken down, we see a different story. Now we have 49 nodes and nearly twice or 3 times the amount of edges, 126 edges. And from this network, we can see that rather than being formed, methanol is more likely to be broken down into another compound. So when we compare these two, we can understand now that methanol production will occur, but there's a higher probability of it breaking down rather than it forming into methanol. And this could be due to just the sheer number of possible reactions that are involved in the methane oxidation process. So, in summary, I'd like to just briefly summarize what we've learned from these networks. First, molecules such as methanol, C2H4 and 6, CH3O, CO, methanol, H2, and water are prominent products of a large number of reactions where the reactions rates vary. From these, we can also see that there are several key intermediate reactions that are invisible to normal detection techniques, and they have a fairly strong influence on the reaction network as a whole. Additionally, we're able to determine that oxygen does not disappear once introduced, and methanol not only forms during the methane oxidation process, but it's also more likely to decompose when in the presence of other molecules. And we also can see is that the low methane conversion is a result of high temperature that is required of the methane activation, plus the large number of reactions that would result in the formation of methane at lower temperatures. So from this, we can understand that by using graph theory, it provides us researchers a new way to analyze chemical reactions and better understand how a potential map would form when traditional experimental and computational investigations fall short. And I'd like to thank you for your attention. And I'd like to thank the support of my research team and my sponsors, as well as the conference for inviting me. Thank you for your attention. And I'm ready to begin to answer questions should there be any. Thank you.
Thank you very much for your presentations. If we have any questions, you can write to my chat session part. Do we have any questions? I think we don't have. Thank you very much, Lauren, for this good presentation. Thank you very much.
Thank you.
Our second presentation title is, let me look at, from Trakya University, Serap Şentürk will present it. Comparison of hydrogen bonds in renewable ionic liquids. It's the DFT-based calculations. Let's see.
Dear Chair, the speaker is joining with a video, and I will play it. And the speaker is on the session, and she will answer the questions about the presentation.
Okay, who will share the video? Excuse me.
Yes, here.
Okay.
Good afternoon, everybody. First of all, I would like to thank organizing committee for this opportunity to present our work and organizing this meeting. And the title of our work is Comparison of Hydrogen Bonds in Renewable Ionic Liquids, EFT-based calculations, Q2AM, NCI analysis. My collaborator is Fatma Kandemirli from Kastamonu University. In this work, the properties, structure, and intermolecular interactions, hydrogen bonding of the proposed model protic ionic liquids in the pure state were studied using the dense functional theory-based calculations. Outlines of my talk: ionic liquids, protic renewable liquids, and proposed renewable protic ionic liquids, materials and methods, results, conclusion. Motif paper. The first motif paper is about the application of ionic liquids And recent years, ionic liquids have great attention because of their energy applications to energy storage and conversion materials and devices. They can use ionic liquids can use for clean and sustainable energy, and also the for electrode catalysis for fuel cells and electrode materials and so on. Ionic liquids are liquids consisting of ions and can be further defined as molten salts having melting points lower than 100 centigrade. And this paper gives the various applications of ionic liquids. Up to date, the best performing ionic liquids are derived from non-renewable sources such as petroleum and natural gas. Due to their potential for large-scale deployment, ionic liquids derived from inexpensive renewable reagents are highly desirable. And first, Shoha et al. Developed a new type of ionic liquids derived from renewable resources, lignin and hemicellulose. The hydrogen phosphate-based ionic liquid is a new type of protic ionic liquid. It has some advantages in comparison with traditional protic ionic liquids. It can be produced from renewable sources at remarkably low cost and applied to industrial level. And on this line, Garcia and co-workers studied the dihydrogen phosphate-based ionic liquid in pure state and its interactions with graphene and carbon nanotubes. They have found that the studied ionic liquid showed remarkable properties and its ability to interact with carbon nanosystems. Those properties can be improved using new families of renewable compounds instead of classic types of ionic liquids with worse environmental, toxicological, and economical profiles. On this slide, we have studied on new renewable ionic liquids. Here, I have presented a part of our research on the subject. We have studied on two renewable protic ionic liquids, namely protonated from the hydrogen phosphate ionic liquid and protonated from hydrogen sulfate ionic liquid. And we have carried out the density functional theory calculations using Gaussian. We have used B3 LYP method and 6.311 G BP basis set. We have analyzed our RDFT calculations using some methods and programs. We have analyzed molecular electrostatic potential map and the quantum theory of atoms in molecules QTAM analysis based on Bader's theory was performed by multi-YPM program. The non-covalent interaction NCI analysis was obtained through multi-YPM program. The RDG scatter pools were created by multi-YPM program, and the color maps of scatter points and isosurfaces of RDG were plotted by GNU plot program and visualized by Visual Molecular Dynamics program package. And let's look at the materials are used to compose of ionic liquids. Ion pairs are in ionic liquids as follows: protonated from the hydrogen phosphate anion and hydrogen sulfate anion. Here, the optimized structures of ion pairs used in forming presented ionic liquids. Ion pairs placed close together for optimization, and after optimization, it has stable geometry with energy minimization. It is the stable geometry for protonated from the hydrogen phosphate ionic liquid. Before optimization, and ion pairs or protonated from hydrogen sulfide ionic liquid close each other before optimization, and the optimized geometry is presented for protonated from hydrogen sulfide ionic liquid. The interaction energy also was calculated, the difference between the total energy of ionic liquid and the sum of the anion and cation energies in the pair structure. Binding energy has also calculated in the same way, but using isolated energies of anion and cation pairs. Let's look at the table 1 about the calculated energies. It can be observed that the interaction energy for the ionic liquid with dehydrogen phosphate is larger than that one with hydrogen sulfide. The same order has found for binding energies. Here is the surface, map surface of protonated from dehydrogenated phosphate. And this map is for protonated from hydrogen sulfide ionic liquid. The color scale indicates charge on the atoms: red, most electronegative; green, neutral; blue, most electropositive. We have calculated the charge analysis also. The ion pairs have less charge values than isolated ones. And we have carried out the QTIM analysis based on electron density at the bond critical points using one multi-YPN program. And in QTIM analysis, we have used some density functions to define the nature of bond characteristics. QTM analysis classifying the bonding characteristics in three groups: for weak and medium strength hydrogen bonding and one valence interactions, for covalent bonding characteristics and the strong hydrogen bonds as the intermediate type of interactions. And the functions in QTIM analysis are electron density of rho var, Laplacian number square rho var density, and the kinetic density G of R, and potential density V of R, and total energy density of H of R, and the ratio of V of R, and divided by G of R. The molecular topographic map for studied ionic liquids is there. In figure 2, atomic mode and bond critical points are presented by purple and orange spheres, and the cage and ring critical points due to the green and yellow surface. The lines are bond tracks. This QTM map for protonated hydrogen phosphate ionic liquid. Bond critical points are between the hydrogen atom of cation as hydrogen H9 and oxygen atom or 13 of anion. Another BCP placed between the O1 and the H10 atoms of cation and the oxygen atom of O11 anion. And it is for the second ionic liquid. And let's look at the QTIM results about the hydrogen bonding. The value of Laplacian of rho for OHO bond for the first ionic liquid is around 0.11. For the second ionic liquid is about 0.12. All these values are higher than the upper values of Laplacian criteria for hydrogen bonding between those values, and as a result, OHO bonds are hydrogen bonds. In order to visualize the QTM results, we have used MCI analysis based on graphs displayed with the reduced gradient density versus the sign of Hessian eigenvalue of lambda2 multiply rho. Here, the RDG scatter plots and isosurface map are shown for ionocloprid with hydrogen sulfate. From figure 4, the strong interaction is shown as blue circle between OHO atoms, and the weak interaction is shown as green circle between OH atoms, as indicated in QTM table 2. This blue circle corresponds to blue region point. That in RDG scatter plots. And this one is the green circle and corresponds to green in the green region. When there was interaction region also. And let's look at the conclusion. The analysis of the interaction data on the ion pairs allows us to make the following ordering. The interaction energy of the ion pairs increases in the order of anions. Also, hydrogen sulfate anions, the interaction energy for the protonated hydrogen sulfate ionic liquid is smaller than the protonated dihydrogen phosphate ionic liquid. It was found that hydrogen bonds of OHO between the ion pairs of both ionic liquids are stronger than OH bonds. Thus, the higher bond energy, hydrogen bond energy values evidences. It's obvious that there is a relationship between the ρ and VFR at the OHO bonds at PCPs. The higher value of the ρ and the more negative VFR values gives the stronger hydrogen bond between cation and anion in the ion pair to be formed. It has found that OHO bond between cation and anion of hydrogen sulfate is stronger than that of the hydrogen phosphate anion. This would stimulate the experimental and purchase studies. The purchase studies, this work will be extended, and a purchase study will be presented at the MSNG conference in July. A yet study on the interactions of acid molecules with 2D polyaniline monosheets. Thanks for your attention.
Thank you very much for your presentation. Do we have any questions? If we have, Serap is here. You can ask
Yes.
your questions from chat part to me, and I can ask her. We have time. We have 3 minutes. I think there is no question. Thank you, Serap. Thank you very
Thank
much.
you very much. Thank you very much to everybody. Thanks.
Our next presentation's name is Pressure-Dependent Structural Elastic Lattice Dynamic and Optical Properties of a Material. It is again a density functional theory approach. Let's listen. Belgin.
Dear Chair,
Dear.
this speaker will joining with a video, and
Okay.
I will share it.
Okay. Okay.
Hi, My name is Belgin Koçak. The title of my presentation is Pressure-Dependent Structural, Elastic, Lattice Dynamical and Optical Properties of Silver Magnesium Fluorine 3, a Density Functional Theory Approach. I would like to start with outline. Firstly, I give you some basic information about our motivation of this study, and then I give the obtained results. The peroxide structure is a huge crystal structure group that includes several subclasses of space groups, including cubic, orthorhombic, tetragonal, rhombohedral, monoclinic, and triclinic crystals. The diversity in the stoichiometry and the structures allow these materials to exhibit a variety of unique properties for many applications, such as high-temperature superconductors, multiferroic materials, magnetoresistors, and topological insulators. The ternary compounds belonging to the group of fluoroperoxides are very stable materials with wide band gaps, and they are considered as a potential candidates for industrial applications in view of their structural and physical properties like photoluminance, piezoelectricity, ferroelectricity, semiconductivity, and antiferromagnetism. These materials have been used in optical application, magnetic tunnel junctions, power storage, semiconductors, lenses, and medical applications. Numerous experimental as well as theoretical research publications were dedicated to the investigations of peroxides. By doing extensive literature survey, we found that not enough data is available about the elastic and lattice dynamical properties of silver magnesium fluorine 3 compounds under high pressure. Some theoretical work has been performed on structural, electronic, optical, and elastic properties using ab initio technique. The aim of this work is to provide a systematic theoretical study of the structural, lattice dynamical, elastic, optical, and electronic properties under high pressure ranging from 0 to 100 gigapascal using the first principle calculations on silver, magnesium, fluorine 3 fluoroperoxides. The computations have been performed by using the Vienna ab initio simulation package. The gradient-corrected functionals in the form of the GGA by Armiento-Madsen 2005 functional are used. AM05 exhibits an excellent structural descriptions of solids. The interactions between ions and electrons are considered by the projector augment wave method. For a plane wave basis, an energy cutoff 700 electron volts is selected. The sampling of the first beryllium zone in the receptive space is obtained using the Moncourt-Peck scheme by taking a 16-16-16 K-mesh, which is adequate for good converge of the calculations. The optimized parameters were calculated by the minimization and full relaxation of the unit cell. The optimized geometric structure of silver magnesium fluorine 3 is shown in figure. This compound belongs to the cubic peroxide structure with space group PM3M and number 221. The atomic position in fluoroperoxide structure under 0 gigapascal are also given in this table. The optimized lattice constant of silver magnesium fluorine 3 is given in table 1. Our results for structural parameters are in good agreement with the available experimental and theoretical study. Our calculated lattice constant value of GGA AM05 is very close to that of experimental values. Figure 2 also shows the effect of pressure on the lattice constants of this compound. It is observed that the lattice constants decrease gradually when the pressure increases. In order to further evaluate the structure stability of this compound under different pressure, we have studied the phonon spectrum. Phonopicode has been used to calculate phonon frequency. The supercells approach has been used to calculate the phonons and 2 - 2 - 2 supercells. Figure 3 shows the phonon spectrum and total phonon density of states for silver, magnesium, fluorine 3 under different pressure. It can be clearly seen that many imaginary frequency exist in 0 and 50 gigapascal, indicating silver, magnesium, fluorine 3 is dynamically unstable in this phase. Elastic properties of a material provide useful information about their hardness, mechanical stability, bonding, and dynamic properties of a material. The elastic constants can be obtained from ground state total energy calculations. The present elastic constants are computed by using the strain-stress relationship. Our obtained results are given in Table 2, which obey Born-Huang stability condition for considered structure. Thus, it can be said that these compounds are mechanically stable at calculated phase. Our calculated results are good agreement with the reported theoretical results at 0 gigapascal. To our knowledge, no experimental elasticity parameters are available for the comparison with this compound. Cauchy pressure can be used to describe the ductility and brightness of materials. If the Cauchy pressure is positive, the material is ductile, otherwise material is brittle. Our results indicate that this studied compound is ductile material. Figure 4 also shows the elastic constants depending on the pressure for silver, magnesium, fluorine 3 compounds. Clearly, all calculated elastic constants show an increase with pressure. It is also noticeable that C11 is more sensitive to pressure, while C44 is the less sensitive to pressure. Table 3 lists the obtained bulk modulus, Scher modulus, Young modulus, Poisson ratio, G to B ratio, and B to G ratio for the silver, magnesium, fluorine 3 compounds. During these calculations of these properties, the Voigt-Race-Hill approximations were used. These properties play an important part in determining the stability and stiffness of the materials. The larger volumes of bulk modulus, Scher modulus, and Young modulus reflect the more incompressible, higher shape changes resistance and higher deformation stability. From Table 3 and Figure 5, the elastic modulus significantly increasing with the pressure, increasing from 0 to 100 gigapascal, which indicates that the compression resistance, shear deformation resistance, and stiffness of this compound can be strengthened by applying appropriate pressure. In engineering, the degree of anisotropy is expressed by the anisotropy factor. If anisotropy factor equals 1, it means that the material is an isotropic crystal. If anisotropy factor deviates from 1, it means that the material is anisotropic crystal. The considered compounds exhibit anisotropic behavior, as can be seen from Figure 6. The anisotropic factors are linearly decreased with the increasing pressure. The Poisson ratio provides information about the bonding character of the material. Poisson's ratio increased significantly with the increasing pressure from 0 to 60 gigapascal for silver, magnesium, fluorine 3 compounds. Poisson ratio also increased slightly with the increasing pressure range 60 to 100 gigapascal. The ratio of Poisson ratio is indicator of ductility or brightness of a material, where vol is higher than 1.75 refers ductility, while lower values indicate brightness. All of the pressure range, Poisson ratio value is higher than 1.75, hence this compound behave a ductile manner. The level of the ductility also increase with pressure. To understand the electronic properties, we have to calculate the bond structure for materials. The obtained results for high symmetry points in the first beryllium zone at ambient pressures are shown in Figure 7. The calculated electronic band structure result shows that title compound is an indirected gap nature at X gamma point. The fundamental band gap for this compound is 2.06 electron volts. The band gap value also increase with increasing pressure. A total and partial density of states are showing in Figure 8. Below the Fermi level, the main contribution comes from the fluorine and silver atom. Above the Fermi level, the band is composed of different states of silver, magnesium, and fluorine. The optical properties of the materials at all photon energies are determined by complex dielectric function. The real part of the electric function describes the electric polarization of the material under the external electric field. The imaginary part of this function is directly related to the band structure of the material. The calculated and imaginary part of the electric function are displayed in these figures. All the optical parameters are calculated in the energy photon ranging from 0 to 50 electron volt at different pressure. The real part of the electric function initially is found to increase with the energy, reach a maximum value after its decrease. It is also noticeable that the real part of the electric function doesn't have a negative value. The imaginary part of the dielectric function also shows the two main peaks. The calculated real and imaginary parts of the complex dielectric function can be utilized to find other optical parameters like reflectivity, refractive index, extinction coefficient, and electron energy loss functions. Our results are displayed in this figure, and this result shows that silver, magnesium, fluorine 3 compound agrees with the literature data. Compared with all optical constants figures, it is found that the pressure has effect on the shape of optical spectrum curves. Briefly, using a first principle calculation based on the density functional theory, the physical properties of silver, magnesium, fluorine 3 fluoride peroxide were studied in a wide pressure range. The ground state properties are optimized using the functional AM05 as a version of GGA. AM05 yield improved and nearly indistinguishable structural properties for this compound in cubic peroxide. The elastic properties show that the studied compound is satisfied mechanical stability within the scope of 0 to 100 gigapascal and ductile in nature. This compound is lattice dynamically unstable in cubic peroxide structure. The band gap nature of this material is an indirect character. And finally, the results in this work can provide detailed information and valuable reference for further experimental work.
Thank you very much for this good presentation. Do we have any questions? You can type your questions to me. I think there's no any question. Thank you, Belgin. Thank you very much.
Thanks. I would like to also thank Yasemin Hocam and all organization team for this lovely organization.
Thank you very much. We also thank them. Let's see what's the name of our next presentation. First principle study of the noble electronic and magnetic properties of the compound. Fatih Ersan from Aydın Adnan Menderes University. Let's listen him.
Okay, let me share my screen. Okay, can you see it?
Yes, we can see.
Okay.
Yes, yes, everything is all right. You can start.
Okay. Hi to everyone. My name is Fatih Ersan. I am from Aydın Adnan Menderes University. I'm studying in physics department as an associate professor, and I want to present our latest study, which is performed by Associate Professor Berna Akgenç from Kırklareli University and Associate Professor Erol Vatansever from 9 Eylül University. First principles study of the novel electronic and magnetic properties of chrome M prime carbon 2. M prime is for titanium, scandium, or vanadium. Firstly, I want to give some information about MXenes and then what is the Janus structures, and maybe one or two sentences for density functional theory and Monte Carlo methods, and then our results about chrome-based Janus structures. I think almost all of us are knowing about the MXenes, the early transition metal nitrides or carbides, which are known as MXenes, just recently entered the research area as a new member of 2D materials after the synthesizing of titanium 3 carbon 2 material. MXenes are important because MXenes are giving hope for obtaining intrinsic 2D magnetism. Nowadays, experimentally, more than 70 MUX phases have been synthesized, and there are millions of possible solid solutions with various MX combinations. And the important thing is desirable magnetic properties of 2D materials can be shown in these MXenes because they have intrinsic magnetism and high spin polarization, and these are depending on the number of d electrons, because as you see, these MXenes are creating with one transition metals and the other one is carbon or nitrogen. I think, okay, that's all. Okay, what is Janus? Janus is in ancient Roman religion and myth, Janus is the god of beginnings, gates, transitions, time, duality, and endings. He is usually depicted like this figure. He is usually depicted as having two faces. One is looking to the past and the other is looking to the future. And are like us, scientists use these Janus faces in materials. And nowadays, these 2D materials are investigating for Janus materials. Recently, different kind of transition metal chalcogenide alloy, which is called a Janus structure, was synthesized, like this slide. In Janus monolayers, even though transition metallic atoms are still sandwiched between chalcogen atoms, the chalcogen atoms on both sides are not identical. It's not sulfur-sulfur, as you see at the end of the right part of the figure. Molybden is sandwiched between selenium and sulfur atoms. To synthesize Janus molybden-based structures, experimentalists prepared triangular molybden disulfur monolayer flakes on sapphire substrates and then stripped off the top layer of sulfur atoms using a hydrogen plasma to obtain molybden sulfur hydrogen structures. And then by thermal salinization of these structures, with the substrate temperature below 450 Celsius, degree, Janus molybdenum sulfur selenide monolayers were obtained. And this is the, I think, beginning of the investigations about 2D Janus materials. And for this study, we used density functional theory and Monte Carlo simulation. We combined these two different methods. Density functional theory is a, computational quantum mechanical modeling method using in physics or chemistry or material science to investigate the electronic structure or magnetic properties or some physical properties about the many body systems. Monte Carlo methods are a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. And we combined these two methodology. And in this slide, you see the top and side view of the chrome 2 carbide structure. For this study, we used like this shaded area, rectangular cell of the chrome-based Janus structure, also for bare chrome, titanium, scandium, or vanadium carbide structures, just to make easy for the magnetic orientations. I will show them, I think, one slide later. And after creating Janus structure with just taking the top layer of the metal atoms and changing it with the other metal atoms, we obtained Janus structures, and then firstly we tested their dynamical stability with using PhonoPhi code. And as you see, there's just a small negative frequency for chrome vanadium carbide, but we are still working on it because it can also depends on Hubbard parameters. If you add Hubbard parameters, probably we can obtain fully positive phonon frequency for chrome vanadium carbide. And the other ones have positive frequencies just for chrome titanium carbide. There's a small negativity, but probably it is related to computational errors. If you use larger supercells, probably they will disappear. And after we obtained their dynamical stability, as I said, with using these rectangular cells, we performed optimization calculations for these 4 different magnetic orientations, which are ferromagnetic. All spin directions are up. The other 3 of them is antiferromagnetic, which are named as Neal, C3P, or zigzag. And you can follow these magnetic orientations from the arrows. And we also perform test calculations for the thermodynamic stability with using WASP package program. In these molecular dynamic calculations, we performed 10 picoseconds, and we obtained, these are the, if I think you can't see my sign, but these top and side view of the chrome vanadium carbide or chrome scandium carbide or chrome titanium carbide, there isn't any reconstruction, there isn't any, namely they are still presenting their bare or their initial cases, and the fluctuation of the energy or the magnetic moments are these in the average, and these green lines show the average of these fluctuations, and they are also similar values with their just optimization calculations. You can see similar values for after these molecular dynamic calculations. And after obtaining the stabilities, we also investigate their electronic structure with performing their density of states calculations. We obtained that all Bayer phases of MXenes are metal, and for the Janus structures, they have different electronic properties. And also, I should note that for chrome 2 carbide, adding Hubbard U parameter changed the electronic structure. For example, without U parameter, there's an inset in chrome 2 carbide. You can follow from that picture. There is an occurred band gap for spin down channel, which obtained with HSC calculations, namely hybrid functional calculations. But adding U parameter slips the energies for whole spin down channel and make chrome 2 carbide the metal. And the other all titanium 2 carbide, vanadium 2 carbide, or scandium 2 carbide are metal. But after creating Janus structures, that I said before, the electronic properties are changing. For example, for chrome scandium carbide shows dilute magnetic semiconductor property, which can be very important to design advanced devices such as spin polarized light emitting diodes, lasers, spin transistors, logic devices. Also, there is I think I should show it from the electronic band structure. For chrome scandium carbide, there is a tiny Dirac-like band dispersion between the gamma and X high symmetry points. And these Dirac-like band dispersions has band gap around 80 milli-electron volts. And for the spin up channel, there is a 580 milli-electron volts band gap. So this is also magnetic material, so we can name it is like a dilute magnetic semiconductor. For chrome titanium carbide, for spin up and spin down channels, for all channels, it shows metallic property, but VBM level, as we can say, as a VBM of spin up channel is only 60 milli-electron volt above the Fermi level, which can be attributed to the semi-metallic property. And for the chrome vanadium carbide, Dirac-like band dispersion, which are located at the gamma and X, between the gamma and X high symmetry points in the spin down channel for chrome titanium carbide and for chrome scandium carbide, is disappearing in chrome vanadium carbide due to the opening of band gap between VBM and CBM. And for spin down channel, chrome vanadium carbide has semiconducting property with a band gap of 270 milli-electron volts, while it shows metallic property for spin up channel. And after we obtained optimized Janus and Bayer mixing phases, as I showed you before, we also performed optimization calculations for different magnetic orientations, and we obtained total energies for that magnetic orientation and for that rectangular cells. And then we compared these energies and obtained J values. J values is spin-spin interactions. And for these spin-spin interactions, we used those values to perform Monte Carlo simulations, and we obtained how the magnetization susceptibility or heat capacities are changing with increasing the temperature. And we obtained that, let me find it because I forget the exact values for the transition temperatures. And we found that chrome 2 carbide is ferromagnetic, metal and ferromagnetic, and the Curie temperature, namely from ferromagnetic phase to paramagnetic phase, the needed temperature is 2000 Kelvin for chrome 2 carbide. And for titanium 2 carbide, we found that antiferromagnetic Neal magnetic orientation is the favorable magnetic orientation, and the Neal temperature is 848 Kelvin. For vanadium 2 carbide, we again found antiferromagnetic Neal is the favorable magnetic configuration, and the Neal temperature is 256 Kelvin. For scandium 2 carbide, we found ferromagnetic, and the Curie temperature is 226 Kelvin. And these susceptibilities or heat capacities also confirm our findings, which are found by DFT and Monte Carlo simulations. These are for Janus structures. For Janus structures, again, similar to the electronic structure, everything is changing in for also magnetic configuration. For example, for chrome 2 carbide has ferromagnetic orientation, or vanadium 2 carbide has antiferromagnetic Neal orientation. Chrome vanadium carbide Janus has Neal magnetic orientation, but due to both of the transition metals have magnetic moment, they show ferromagnetic behavior, and the transition temperature is 918 Kelvin. Again, chrome scandium carbide shows Neal magnetic orientation with ferromagnetic ferromagnetism, and the transition is 1120 Kelvin.
Excuse me,
Yes?
is it possible to come to the end?
Yeah, okay.
Please.
I'm finished.
Thank you very much.
And at last, chrome titanium carbide, it shows C3p phase, and again ferromagnetic, and the transition is again 1110 Kelvin. This is the conclusions, but I just say these numbers. So I want to thanks to my collaborators, also TÜBİTAK. This is an TÜBİTAK project, and thank you for listening to me.
Thank you very much for this important presentation. Do we have any questions? We thank Fatih Ersan. Thank you very much.
Thank you.
Let's see our next presentation name. Thickness dependent electronic and piezoelectronic properties of 2D black arsenic and black phosphorus. Berna Akgenç will present this presentation. Let's listen her.
Could you hear me? Could you hear me?
Yes, Berna,
Okay.
I can hear you.
Okay.
Okay.
But I couldn't see me, I think. I tried to open the video, but I couldn't success.
Let me try. Berna. Okay.
Okay.
I see.
Hi, everyone. Okay. Hi, everyone. My name is Berna Akgenç. I am Associate Professor Doctor at Kırklareli University. Today, I am going to talk about thickness-dependent electronic and piezoelectric properties of 2D black arsenic and black phosphorus. This is my outline of the speech. I will give what's the meaning of 2D materials, and I will try to give example of thickness-dependent physical properties from literature. What was our motivation and what we choose as methodology, and I will give my result. I will start from optimized geometrical structure of black arsenic and black phosphorus, and I will continue with electronic properties and piezoelectric properties, and I will sum up with acknowledge. Okay. I think after Einstein getting a Nobel Prize, the most famous Nobel Prize came to 2010 to Andre Geim and Nova Saleh. Everybody knows what is the graphene and their extraordinary properties. After discovery of graphene, scientists try to find an alternative to the material. They search from the nature and they try to find an alternative graphene. They find hexagonal boron nitride, transition metal decalcolagen, and MaxSyn, and so on. In this topic, in this speech, I will try to give black phosphorus. It's like this structure, and the cousin of the black phosphorus named as black arsenic. I will try to give these two structure. The 2D materials exhibit advantage properties. The most famous one, again, electronic properties using a spintronic application. Electronic properties is ranging from metallic to semi-metallic, semiconductor to insulating. They are two huge tunable electronic properties. And atomic thickness offers maximum mechanical flexibility and surface accessibility. And large literal size combined with nanometer thickness allow for high surface area available for ion absorption and surface reaction. If you look at the Web of Science or Google Scholar, if you write it down, thickness-dependent physical properties, you can find thousands studies published until now. I will try to give some random example from the literature. The scientists are focused on the find physical properties related to thickness dependent. As an example here, I will give the platinum-based transition metal decalculation. It's published in EPG 2D Materials and Application 2019. As you see from the structure, those are the platinum-based transition metal decalculation. It's again yellow structure. Fatih Arslan was talking about what is the mean yellow structure. They created like this structure and they give electronic properties from 1 layer to 10 layer. As you see the electronic band structure, they changing and they narrowing and they smaller and so on. Here, another example, germanium phosphoride, because germanium phosphoride is using field effect transistor devices, using P-type germanium phosphoride nanosheet of various thickness. As you see from the figure, valence band maximum and conduction band minimum position from 1 to 4 layer relative to vacuum level. As number of layers decreases, the VBM is lowered while CBM is destabilized. This study can stimulate further research on the new 2D semiconductor materials and so on. Another study is another colleague also, Mehmet Yağmurcu Kardeş studies here. He also look at the thickness dependent lead diode. He look at the electronic properties and also Raman spectrum. As you see, this is the thickness dependent Raman spectrum. He showed that two predominant peaks, A1G and EG, exhibit phonon hardening with an increasing number of layers due to interlayer of van der Waals interaction. This is another study. And also the last example from the literature, I will give the black arsenic. It is also published Advanced Materials 2018. They also look at the Raman spectroscopy. They show that while the thickness of black arsenic decreases from bulk to monolayer, the blue shift of these two peaks, it's called AG and AG modes, are observed. At the same time, the intensity of these two peaks gradually weakened as the decrease of sample of thickness. I give this result, I give these papers as an example because I will try to highlight too many people, too many scientists working on the thickness dependent physical properties. Okay, what we are studying this study, what was our motivation? We faced this paper, it's published Advanced Materials 2019, I think, two years ago. They calculated piezoelectric response in multi-layer black phosphorus for piezotronic and nanogenerators. This paper is an experimental study. They give that this is when you multiply black phosphorus, you can use piezoelectric response, and you can use it piezotronic or nanogenerator. Okay, we say that, okay, we know black arsenic is cousin of the black phosphorus. If we calculate black arsenic as like this, I mean, the thickness dependent, if we created monolayer, bilayer, trilayer as in black arsenic, can we get tunable thickness dependent? If we succeed to tunable thickness dependent, I mean, it should be semiconductor. And after getting the semiconductor, if we say, okay, those are all of them is semiconductor, we can check the piezoelectric properties. And it was our motivation. We started from that. We used computational material science. Actually, we are not doing the experiment in the laboratory. We are doing experiment in the computers. We use, of course, we are trying to solve Schrödinger equation. If we solve Schrödinger equation, you can know every property, each properties for the structure, but it is like an impossible, is an analytically. Everybody knows that some tools help us to solving the Schrödinger equation. we used density functional theory. What was the density functional theory? Actually, the theory is trying to find the initial gas. We call density electronic density, and then we calculate effective potential, and then solving Kohn-Sham equation and evaluate electron density and total energy. If we converge according to our initial parameter, I mean input file, everybody knows input file. According to input file, if it is converged, our answer is yes, that means you get output file. If the answer is no, that means your initial gas is wrong, and you should try the best, more accurate initial gas, and it is continue to finding the converge. This is the basic of scheme of the density functional theory. This is our preliminary result. Actually, we didn't publish yet. We are still continuous on this study. We have still problem. We are still challenged in this problem. First of all, we optimize geometrical structure of black arsenic and black phosphorus. As you see from the top wave, and this is the top wave, those are the side wave. We created monolayer black arsenic. Black phosphorus is completely the same. You just change atoms, arsenic and phosphorus. The structure is completely the same. We created monolayer of black arsenic, and then we put extra layer. It means bilayer black arsenic. After optimized bilayer, we put extra thickness, extra layer. It's a 3 layer. We continue to 6 layer. As you see from our results, we get we get lattice parameter for arsenic for 1 layer to 6 layer, and arsenic black conventional bulk structure of arsenic, and we repeated same structure for phosphorus, black phosphorus, from monolayer to 6 layer, and we also check the bulk structure. As you see, there is no C dimension for the 2D materials, and as this is the bulk structure. Again, for phosphoran, there is no C dimension for the 2D materials. Again, the bulk structure is C comes from here. As you see, there is an A int. What does that mean? Those are van der Waals. The van der Waals interaction is too effective in this heterobilayer. We also calculated interlayer energy is here. And also AG means band gap. As you see from the monolayer to bulk, the band gap is getting narrow. And again, phosphorus band gap is getting smaller. That means here the figure is top side for arsenic, down below side is for phosphoran. You couldn't see my mouse, I think, but as you see from arsenic, monolayer arsenic, it has show indirect band gap. The rest of them is direct band gap. What was our motivation? If we turn back to our motivation, we should get semiconductor material. As you see from the electronic band gap, okay, they keep semiconductor behavior. It's also tunable. It is good. This is one of our output. And also, I will try to explain what does that mean, piezoelectric effect. Piezoelectric effect is related to mechanical stability and electric field, or vice versa. When you when you apply the strain, the crystal is create electric field, or vice versa. Those are the piezoelectric tensor. EEG is represented XYZ. This is the strain tensor. Those are the stress tensor. The experimentalist doesn't give strain tensor. They gives us D. if you check the piezoelectric response in the laboratory, you should get D. But in the computational tool, you can just give the E. But there is a relationship between E and D with the elastic tensor. Here is the elastic tensor and strain, piezoelectric strain tensor, and you get the stress tensor. Here is actually a piezoelectric effect animation. This is the positive charge. You can think about this is the silicium atom. The red one is the oxygen atom. When you push the positively charged, they little bit outside. The structure goes outside, and the center of the position little bit upstairs. They created the dipole, electrical dipole, and it gives us the electrical response. This is the really good animation for the understanding the deep of piezoelectric response. Here is the another output. Here is the another output table. As you see, black arsenic in monolayer and bilayer, we couldn't get any piezoelectric response. And if you increasing the number of thickness, you get piezoelectric response. It is good. It is the one of the output. That means it is a tunable. Let's say if you are need the piezoelectric response, that means you should have minimum 3 layer of black arsenic and so on. This is the one of the our output output. And also we calculated elastic tensor of arsenic. As you see from the table, C11 is the elastic tensor. It's dramatically decreases from monolayer to 6 layer. Those are the this is the another output file. We have planning to search vibrational properties as well. Because we have accepted some modes, and we have expected some modes. We have still working on it. I will thank you to join, but I will first thanks to my colleague Mehmet Yağmurcu kardeş from İzmir Institute of Technology. Another colleague is Fatih Arslan, Aydın Adnan Menderes University, and all computational sources were provided to TÜBİTAK ULAKBİM. We appreciate it for that. Thank you for attention.
Berna, thank you. These are important new topics. Thank you very much for studying these things. Do we have any question? Berna, thank you very much.
Thank you, Engin Hocam.
See you.
See you. Bye.
Our last topic, let's see the name of our last topic. Investigation of structural, mechanical, electronic, and dynamic properties of Hausler material compound as a material, let's see the name of it now, by AB initial method. Hatice Tekin will present from which university? From Gazi University. Let's listen her.
Dear Chair, this
Hi.
speaker is joining with a video.
Okay.
Hello, I'm Hatice. Investigation of structural, mechanical, electronic, and dynamic of half-Euler cobalt titanium phosphate compound by aviation method. Outline, motivation, calculation method, structure properties, electronic properties, elastic properties, and conclusion. Motivation. Magnesium arsenic structure half Euler compound show very interesting physical properties. One of the characteristics that Euler-type alloys are known for which makes them attractive in a technology is that they have a shape memory effect. Magnetic sensor, magnetic memorized, spintronic are some of the application areas. It is also used in the production of tunneling, magnetic resistance, polarized line meeting LED, and spin injection devices. Good thermoelectric material when they have a narrow forbidden energy range. If the total number of valence electrons in a primitive unit cell is 18, half-Euler compound have a band gap and show thermoelectric properties. The thermoelectric linked transport properties of 36 half-Euler compound have theoretically been stated in recent years. But the mechanical, dynamic, and optical properties semiconductor compound of the technological important 1.4 electrovolt forbidden energy range have not yet been stated. First principle calculation. It is based on quantum mechanics. With this method, the molecular structure and related properties can be calculated. It doesn't need any experimental data and output. YDFT explain basic physical properties. It is computation easy. The three-dimensional electronic density distribution of N can be handled more easily than the three-dimensional wave functions PCR. In addition to infinite-dimensional periodic system, systems that contain a large number of atoms and are not periodic can also be considered. In this, the energy of the system in terms of density function. Many practical problems. Schrödinger equation for a time-independent multi-particle system. Hamiltonian of the system consisting of nuclei and electronic interacting a crystal. Calcium equation defines the system of non-interaction particles. The electron density R is defined as the variable. The fundamental state properties are denoted by a function of the fundamental state electron density. If the basic state electron density is known, other basic states are also known. Approach to exchange correlation energy. It is not possible to accurately collate the change and exchange correlation energy of R. Since the form of this term is unknown, it is difficult to write the density functionally. But there are many approaches to solving this energy. At the beginning of them, local density approach, generalized gradient approach. Pseudopotential. Systematic representation of all electronic and pseudopotential and their accompanying wave function. Calculation method. WASP and GGA-PPA and the energy cutoff for the plane wave basic set. Phonon frequencies are calculated by phonopic code. Finding in this study a half-Euler compound, cobalt, titanium phosphate, magnesium arsenic with some of the structural electronic elastic properties and electronic structure and dynamic properties of the base, which is an effective method in the determination of the states of density functional theory and plane wave pseudopotential based on a Vinci method more calculated. A visual code for the calculation was visible packet program. Our compound have been studied under the generalized gradient approach and the local density approach. The theoretical crystal structure in equilibrium is determined by minimizing the Hellman-Fermi forces on the atom and the stress on the unit cell. Energy conversion was optimized by taking 10 electrovolt atom. Structural properties. Bulk model of cobalt titanium phosphate compound together with mesh constant and pressure derived of bulk model were obtained using the following equation. The obtained result of indicated compound are given in the table and compared with the available theoretical result. Bulk model and first derivative of bulk model is obtained by performing energy calculation with different volume and fit them in Morgan state equation. Formation energy equation is obtained 1.440. The volume indicate that the structure is stable. Also indicate that it can be experimental stabilized. Elastic properties. Second order elastic constant were calculated using the strain correlation. Furthermore, the mechanical stability for the cubic structure crystal was evaluated with the generalized Bornholm elastic. The elastic constant we found provide the criteria for the Bornholm elastic constant. Our compound is mechanically stable. The elastic constant of solid correlated the mechanical and dynamic behavior of the crystal and informed the nature of the forces working the solid. In particular, they give information about the stability of of the material. The elastic constant of C are fundamental and indispensable for defining a mechanical properties material. The elastic constant we found provide the criteria for the Bornholm elastic constant. Our compound is mechanically stable. The high values of the Young model and the Scher model indicate that the material is a hard metal. There are different methods to understand whether the material is ductile or bed. One of the methods is to determine the G-B ratio. The Scher model G and B book model B represent the resistance, the plastic deformation in fracture resistance, respectively. A second model is the gauge pressure. This parameter defines in the enclave properties atomic bond, metal, and compound. One important point to note, gauge has a composite metallic bonding character and ductile if the pressure positive. Gauge press and G-B ratio are compatible. The third method, we can explain whether a material is ductile of the birth position ratio. The position ratio is less than 0.26 for buried material, otherwise is the ductile. As can be seen from electronic feature. Indirect band space semiconductor. In order to make sense of the electronic behavior of this compound, we have computed electronic band structure as shown in. It can be concluded that the valence band maximum occurred at the gamma point, while the conduction band minimum located at the K point for the cobalt titanium phosphate compound. These indicate that cobalt titanium phosphate compound is an indicated band gap semiconductor. Total and partial state density, charge density map per plane. The total and partial density of states are also plotted figure 4. Clearly, the valence band are located rates. The first and second region of valence band originated from hybridization of the type states and pp states. Vibration properties. Phonofrequencies of cobalt titanium phosphate were calculated with Phonopy code. Phonopy is an open search code for phonon bait calculation. It has been described the dynamical properties of material at fine temperatures in this code. Phonon dispersion curves for the cobalt titanium compound are shown in figure 3. There is no imaginary phonon frequency in the beryllium region confirming the dynamic stability of the cobalt titanium phosphate compound. Since the cobalt titanium phosphate compound has 3 atoms, it shows name phonon branch, 3 of which are acoustic branch and the other 6 are optical phonon branch. On the right side of phonon curves and figure 3, the corresponding total density of phonon states for this compound show. Thank you listening to me.
We have come to the end of our presentations. Do we have any questions? Thank you very much for listening. Thank you.
Thank you.
Thank you very much to the organization members for their effort. I'm closing the session. Thank you very much.